so I'll give the announcement at 2. Okay. Well, good afternoon and welcome everyone here in our studio audience. Thanks so much for coming to see our broadcast of the total solar eclipse. Are you Totality excited? Yeah. That sounds pretty good. Hopefully it gets a bit better by about 1:38 when Totality happens. So we are now streaming live all across the internet on all the social channels, so it's out there. This is going to be about the last time that I'm talking to you directly. Most of the show is going to be looking at these cameras, so just be aware of that. Don't feel left out. But we're so glad you're here to witness this with us, and so thanks for being such a great audience. For 50 years and going, the Exploratorium is dedicated to bringing people up close to phenomena in science, art, and human perception. All those things start with making observations and asking questions, and that's exactly what we're going to do today as we bring you one of the most spectacular and astounding events the skies have to offer us, a total solar eclipse. My name is Sam Sharkland, and I'm coming to you live from Pier 15 at the Exploratorium in San Francisco, where we're going to be looking at the total solar eclipse. Look at this beautiful audience out there. So not only are we here, but this live stream is thanks to the telescopes that we have out in the field in the mountains of the Coquimbo region in Chile. Thanks to our crew, this is one of the best viewing spots to see the total solar eclipse, so we expect a clear view of when the moon covers the sun in just a matter of time. So what is a total solar eclipse? Well, in most basic terms, it's when the moon comes in between the sun and the earth, thereby casting a shadow. Today, the shadow is moving all the way across the Pacific, is going to hit land there on Chile's coast and go across the rest of South America. The Exploratorium has been broadcasting from the shadow of the moon of the eclipse since 1999. 2 years ago in 2017, during the Great American Eclipse, we were in 2 locations, one in Oregon and one in Wyoming, to experience totality with thousands and thousands of other Americans who were also enjoying the eclipse. This is something that's not to be missed, which is one of the reasons we broadcast it. The next time a total solar eclipse is going to be in North America will be 2024, so make your plans now. One thing to note, though, when looking at the sun or observing total solar eclipse, never, ever look at the sun without certified eye protection or filters. You'll notice in the video everyone's wearing them because that's going to protect you and keep your eyes safe until that moment of totality. To learn more safe viewing techniques or to follow us along on your phone, you can download our Total Solar Eclipse app on either your iPhone or your Android. But let's get started. To help get us some context about what we're going to see during the eclipse, we're going to bring out our co-host. He was with us in the field in Wyoming in 2017. Hakim is an astrophysicist with the Florida Institute of Technology, and we're so thrilled that he's joining us back out here on stage today for today's total solar eclipse. Now, Hakim,
Yes.
we were just looking at that telescope image of the sun, and I already noticed that the disk of the moon is pretty much about halfway across the sun. Can you tell us about where we are in this eclipse?
Well, we are about 36 minutes from totality, and it turns out that eclipses have their own language, right? So we speak in terms of contacts. So imagine two different circles, one bigger, one smaller, and if I slide them past one another, their edges will make contact 4 times. So the beginning of the eclipse happens when you make first contact, but that's not totality. Totality begins at second contact, when the leading edge of the moon reaches the far edge of the sun, and then because the moon's disk is a little bigger, it takes a little bit of time, and that is the duration of totality. And then when it passes all the way to the other side, that's fourth contact, and the eclipse is over, and that whole process will take about 2 hours and 20 some odd minutes.
Wow, so we're just in the beginning phases, and it looks like we wouldn't be able to get those precise views of contact first, second, or third without the telescopes that we're looking at now. So we actually have 4 telescopes out in the field. Can you tell us what those different views that we're looking at are?
Yeah, we're looking at 2 different types of light coming from the sun. So we have white light and we have hydrogen H-alpha light, and they let us see different parts of the sun. The white light allows us to see what we call the surface or the photosphere, and the H-alpha allows us to see the chromosphere, which is actually at a higher altitude and hotter. And we have a wide field and a close-up for both types of light.
So in this white light, I do see some dark spots, and of course that's not the sun right now, but what is this white light view allowing us to see?
Well, we see what we call the surface, the photosphere, and so we see big sunspots there. They are the main feature of the photosphere in the sun.
And the telescopes with the hydrogen filter?
Yeah, well, that allows us to see the chromosphere. So you see that the 2 images kind of matched up. It's sort of the same stuff, only at a higher altitude. So this material has been heated to about 8,000 degrees or so, whereas the surface is about 2,500 degrees cooler.
So it's even hotter on the surface rather than the higher altitude?
No, the higher altitude is hotter than at the surface. So if you look at the sun, we talk about from the surface moving up different layers. They're not really layers, they're more like structures, but you have the photosphere, which is the surface. We have the chromosphere, which is hotter in the thousands to tens of thousands degrees. Then we have the corona, which is 2 million degrees, and in certain events can get up to 10 or 20 million degrees.
That's incredible.
That's nuts.
It just so happens today that we have the telescopes in a very special location. Our telescopes are in good company up in the mountain that we showed you earlier. There it is there. Can you tell us about from where we're observing?
Yeah, so this is at the National Science Foundation's Cerro Tololo Inter-American Observatory down in the Coquimbo region of Chile, northern Chile. So these telescopes, CTIO, stands for Cerro Tololo Inter-American Observatory, and it is at 7,200 feet altitude. It's run by it's a site of America's National Optical Astronomy Observatory. It's run by the American Universities for Research in Astronomy under a cooperative agreement from the National Science Foundation. So the NSF supports America's ground-based astronomy efforts, while NASA supports America's space-based astronomy efforts.
And this region, that's really known for its stargazing. They call it Root of the Stars. There's over 300 clear nights. There's all sorts of observatories over there, many run by families. So it's really a whole community that gets to embrace this astronomical investigations that we're looking at there. And it just so happens that these folks are lucky enough to be in the path of totality today. Can you tell us about where the shadow's landing?
Yeah, that's right. So when you see the shadow of the moon fall on Earth, it doesn't hit everywhere at once. You have to be at just the right location. And we call this the path of totality. So if you look at our illustration, you see a red line in the center. That's where you have the maximum totality. And then there are these lines on either side that show you the limits of totality. And that's when the alignment between you, the moon, and the Earth are right. So you get you block out the sun completely.
So this view is from 2017, and this is actual satellite imagery, right?
That's right. This is from the EPIC instrument at an altitude of 1 million miles. And you see the actual shadow of the moon on the Earth's surface as seen by the satellite.
And there's a difference between being right in the center of that shadow versus on the edge, right?
That's right. So there's a saying that it goes like this. The difference between a partial solar eclipse and a total solar eclipse is like the difference between a lightning bug and lightning. Right? 99% is not 100%. So we see a partial solar eclipse where the sun is not completely covered because alignment isn't perfect. So people outside the line of totality can get a partial, or if you're far away like we are in San Francisco, you don't see any eclipse eclipse at all.
Not at all. Well, thank you so much for that
Thank you.
primer, Hakim. We're going to excuse you for the moment,
All right.
but bring you back up. I'd like to see the telescope feed if we have it. Might not be up right now, but perhaps we have the Chile cam. A lot of this is abstract, hard to grasp unless you're there, but thankfully at the Exploratorium we have some of the best educators in the country. So 3 of them are going to come out today and give hands-on science demonstrations to show us exactly some of the mechanics of how the total solar eclipse works. All these educators are part of the Exploratorium Teacher Institute, and Teacher Institute is currently in session now, where they're giving current middle and high school educators the skills to meet the next generation science standards. So it's really exciting work we're having here. First up, Exploratorium Senior Scientist Julie Yu will tell us a little bit more about the shadows.
Thanks, Sam. So as Sam mentioned at the top of the show, an eclipse happens when the Earth, the Moon, and the Sun all line up in the straight line. This is really easy to simulate at home. Here I have my globe, and for this size Earth, this black ball represents the correct size of the corresponding moon. The moon's diameter is about 1/4 the diameter of the Earth. So I have a light off to the side, and you can see that when the moon gets just right in between the Earth and the Sun, it casts a shadow. And as Sam and Hakim just mentioned, the shadow doesn't cover the entire Earth. It only covers one part of the Earth. And the darkest part of the shadow, the umbra, is where people will experience a total solar eclipse. Some people will experience a partial shadow. They'll be in the penumbra, and they won't see the whole thing. They'll see part of the sun blocked. Now, just like standing in the shadow of a tree or a building feels shady and cool, standing in the shadow of the moon is shady and cool, but it's magnified so much because the moon blocks out all of the sun. And so it gets really cool and spooky, and all the light is blocked out to that part. It's important to remember that these things are in constant motion, and in 3 dimensions. The Earth is rotating and revolving around the sun, and the moon is rotating around the Earth. So that moment where all 3 objects line up in a line is one of my favorite words in astronomy. It's called syzygy. And that moment of alignment is where people will experience the total solar eclipse. And that moment isn't fixed in time. It's constantly moving, and we call that path of motion the path of totality. And an important thing in thinking about eclipses is to understand the size and the scale of them. And I've been holding this moon pretty close to the Earth, but at this size, the moon should actually be 30 feet off to the side, which is way bigger than the size of this stage. So I have a much smaller Earth here and its corresponding moon, which is really dinky. And at this size, these 2 objects at the correct scale would only be 5 feet apart. And so this tiny moon will cast a shadow on one small spot of Earth, and folks in that small spot are the lucky ones who are going to experience a total solar eclipse. You may be wondering, how can such a tiny moon block out the entire sun? Well, fortunately, we have our senior physics educator, Dr. Desiree Whitmore, here to help us understand that. Desiree?
Thank you, Julie. So the question that Julie just asked is, how can you have a moon that is so tiny that happens to be 1/4 the size of an Earth, right? So I can fit 4 moon diameters across the diameter of my Earth. How can that block out the sun? How big is the sun? The sun is actually 100 Earth diameters wide. I don't have a model for that because that would be way too big to fit onto this stage, unfortunately. So the question becomes, how can a moon block out an object in the sky that is 400 times bigger than it? And the answer is actually because of distance. So as Julie mentioned, the moon is actually about 100 moon diameters away from the Earth. The sun is also 100 sun diameters away from the Earth. And so the key here is all about angle. When you look at things in the sky, you might have noticed in your daily interactions that when you walk away from something, the object gets smaller. Now, here, as you are going to walk away from the sun, we're going to walk away 100 solar diameters away from the sun. I'm going to have Sam help me here. So if you have the sun here, while the sun is in the sky, you're going to measure, using geometry, something called angular diameter. So you're going to take the diameter of the sun, and you're going to divide it by the distance that the sun is away from the Earth. In our case, it's 100 Earth diameters. So here on Earth, it's making this angle for me to see the sun. Now, because it's 1 over 100, that means that it's 0.01 radians, or half a degree. Obviously, this is more than half a degree, but if I was going to move away 100 times, you wouldn't see me on the stage, right? So here is my moon now, and my moon has the same ratio as my sun. And so when I have the moon coming into syzygy, or in alignment, here I'm the Earth, I have my moon coming in, and it makes the exact same angle as the sun does, and it's able to completely block out all light from the sun. Now, this happens not as often, thank you, Sam, as you would think. I mean, you might be asking yourself, the moon revolves around the Earth every single month, so why don't we have an eclipse every month? Well, our senior science educator, Eric Muller, is going to come out and explain that to you now. Eric?
Thanks. So, as Desiree was pointing out, is that you would think maybe an eclipse happens every month, but it doesn't. And it doesn't because these two terms. One term is called lunar nodes, great term, and the other term is called syzygy, which you've been hearing a lot of. I am going to show you a model which will hopefully explain why you don't get eclipses every single month, and my model is not going to be to scale. So on my model over here, I'm going to use these cups. And on my model, here is the sun, obviously not to scale with the Earth, but here is the Earth. The Earth spins around once per day. And also the Earth is actually tilted at 23.5 degrees. So this model has a couple of faults here and there, but it will help. So it spins around, that's once per day. And when it goes around 365 times, it works its way around the sun. The interesting thing is when it works its way around the sun, you can notice it kind of makes this disk that goes around. This disk, or this plane, is called the plane of the ecliptic. All the other planets are in this same plane over here. So now we're going to put the moon into this model. So here's the moon, and I'm going to stick my moon on to another cup right there. And the moon goes around the Earth. And it takes about 28 days or so to go around. And it goes around the sun. But as I'm doing this, you can see, wow, look, it's right on that same plane there on the ecliptic. It should be an eclipse there, and it should be another eclipse, a lunar eclipse there. But it doesn't work like that. Turns out that the moon doesn't revolve around on the same ecliptic plane. So I'm going to put the moon in a different position. Turns out that the moon is actually on a tilted orbit a little bit more than 5 degrees. So here is my lunar orbit over here. So this will go around the sun, and you can notice, if I hold that, this lunar orbit over here stays in roughly the same position. This is the plane of the lunar orbit. This is the plane of the ecliptic, and you can notice that they're off from each other. So it turns out that when the moon is over here, it's way off from the ecliptic. And obviously it's on the back side, so there's not going to be an eclipse there. When it's over here, it's way below the Earth. It only can make an eclipse if it's right in line over here. So this orbit over here needs to be right on the same line. So this is called the lunar node, when the plane of the ecliptic and this lunar plane kind of meet up. And it'll happen here, and it'll happen here. But still, no lunar eclipse. It only happens when the moon is right at that node. That is syzygy, when they are in line. So there'll be a potential eclipse then, and there'll be a potential eclipse right about there. Syzygy, and when the lunar nodes line up. That's why you don't have eclipses every month. Thanks.
Thank you so much, Eric, for bringing some hands-on science to us. These simple demonstrations you can find more of online at exploratorium.edu called Science Snacks. We have a whole library of them for you to check out. But we're here back on the telescope feed live from Chile. Already, I'm noticing a big difference of where that shadow of the moon is in front of the sun. I feel like I can almost see the diameter there. And talking about the eclipse is different than experiencing the eclipse. So that's why our next presenter, Ron Hipschman, has been with the Exploratorium for 48 years, and he has been in the shadow of the moon and the path of totality at least 5 times and has helped us broadcast eclipses since 1999. So Ron is one of our experts on eclipses, and now he's going to talk us a bit more through about what one would experience if they are in the path of totality. Ron?
Thank you, Sam. Because of the Exploratorium, I've had the opportunity to go and actually experience these amazing events, and I encourage everybody to go and visit an actual solar eclipse yourself. Watching it on the screen is exciting, but watching it in real life is amazing. So what can you possibly see during a total solar eclipse? Well, there are the partial phases, which is what we are seeing right now. The partial phase, when the moon first moves in front of the sun. That's called first contact, when that first little bite is taken out. It covers more and more and more of the sun over the next, in this case, hour and 10 minutes today. And when you get about right here, you begin to notice things if you're actually at the eclipse. It's getting darker. The environment around you is really changing. It's getting darker, but not in the same way that it does when the sun sets in the sky, because when it does that, the sun's turning orange and red, and it's tinting the entire landscape. Here, during partial phases of the eclipse, it's just getting gray, and that's kind of weird. You got a kind of weird feeling inside you that something is wrong. Here we're taking another look at where we are at the partial phases. If we come back to my slide, we're going to continue a little bit further. And here we see Julie, as a matter of fact, up in Madras, Oregon, and she's holding up a piece of pegboard. You want to take an advantage of these partial phases and see them with a pinhole projection, the safest way to do it. And here she has a piece of pegboard, and we're casting a shadow on a piece of white cardboard. And if we magnify, zoom in on that cardboard there, you'll see that every hole in the pegboard is making a little image of the sun, of the partially eclipsed sun. Perfectly safe way to view the partial eclipses. You can use anything. Pegboard is one thing. Thanks to all of our NASA sponsors in Oregon, this is Kristen, one of our NASA sponsors, who brought her colander with her. And so the colander has a bunch of little holes in it. And if you zoom in on the colander, you see that every hole in the colander is also making a little tiny image of the sun. So just bring along stuff that has lots of holes in it. You can also just use your hands. If you cross your hands like this, you make pinholes between your fingers, and the pinholes between your fingers also make little images of the sun. So going back to that partially eclipsed sun, as we get further and further into the eclipse, it gets darker and darker and darker. You don't really notice it happening until about right here, and then as you continue, you can actually see it get darker. You can feel the temperature change. You can actually watch the environment get darker as it happens. So if we go back now, and we see this slide as it gets the last little bit of the sun to disappear, you begin to see the corona, and the last bit of sun to disappear is called the diamond ring effect. There's the last little bit of sun peeking out from behind the moon. Here's where you can actually whip off your glasses and look at the sun, and you get to see the corona in its full glory. Now, one little effect that a lot of people miss is that the last bit of the sun disappears behind the moon. It breaks up into these little beads of light because the edge of the moon is not smooth, it's mountainous. It breaks the edge of the sun up into little segments of the sun. This was first noticed during a eclipse of the sun in 1836 by an astronomer named Francis Baily, and so these are now called Baily's beads. If we look at the sun here, the moon rather, you can see the black edge there is an exaggeration of the edge of the moon during this eclipse. So you can see that There are places where the mountains stick up and the valleys have kind of dip down, and that's what creates these Baily's beads. And here's a computer simulation done of it by a free computer program which you can download called Solar Eclipse Maestro. And if we set this in motion, you can see the last little bit of the sun disappear on the lower left-hand side of the screen, the last Baily's beads, but also you'll notice once the Baily's beads are gone, there's a reddish edge there, and that's the outer atmosphere of the sun. It's glowing hydrogen gas. It's kind of this crimson color, and then it goes behind the moon completely and emerges a little bit later on the lower right-hand side, and so you begin to see the chromosphere, that red atmosphere of the sun peeking out, and then Baily's beads at that C3 point, third contact point, reappearing. Now, if we look at this a little bit more closely, I'm going to rotate that C2 point, the second contact point, the lower left-hand side to the top here, and we can watch as the sun disappears below the horizon of the moon, and we can see this is what the Baily's beads will look like for this particular eclipse. It's different for every eclipse. This is again predicted by a computer simulation. And once all of those bright white bits of the sun, the photosphere of the sun disappears, we'll be able to see the sun and the corona. Now here's an exposure taken just after Baily's beads disappears. You can still see that beautiful chromosphere, that glowing hydrogen gas on the edge of the sun, and that is just a beautiful sight. That's the color. If you put hydrogen in a vacuum tube and made it glow with high voltage, that's the color you see of glowing hydrogen gas. And you also see on the edge prominences. These are fountains of hydrogen gas, the same color as the chromosphere. If we expose the camera a little bit more. Now your eyes, you don't have to do this because your eyes can see a wide range of brightnesses, but cameras are not as good. You can begin to see the inner corona here, and it's not just a uniform spread of light here. It's twisted into streamers and these very twisted forms on the edge of the sun, and those are formed from the magnetic field of the sun. If we expose a little bit more, we can see the outer corona. This is all from the same eclipse. Your eyes will be able to see all that all at once. And one thing you might want to look at during a totality is to look at the sky. I know you want to look at this beautiful sun the whole time, but if you look at the sky actually it gets dark, and you'll see the stars and planets come out. So this is the sky as seen from Chile. And let's magnify in on the sun, which is on the eclipse sun, which is in the lower left-hand side there. And there you can see the eclipse sun, and on to the left of that, you'll see Venus very close to the horizon. We may be able to see that. And to the left, to the right of that, you'll see Mercury and Mars. And the bright circle of winter stars up there, Betelgeuse and Rigel and Procyon and Castor and Pollux will be up there too. Normally those stars are only seen during the winter. The sun's in front of them. But during an eclipse, you can see them during the middle of the summer. So at the end of the eclipse, Baily's beads come out again. Now here we've taken the Baily's beads, rotated them to the top here so we can see it a little bit easier. And the first appearance of Baily's beads means you can no longer look at the sun anymore. You have to put on your glasses, look at them again through your glasses, because the sun's way too bright. It'll burn your retinas. And of course, this also means the return of the diamond ring effect on the other side of the sun, and we get to watch the partial phases as the sun is revealed from behind the moon, and that takes about, again, an hour and 10 minutes or so. Now, when I was in Africa, weather was a really important thing. This was in 1980. I was in Africa, and during the eclipse, it gets a lot colder than it is on the either side of the eclipse, and so if you have an environment like in Africa where it's humid and there's a lot of water in the atmosphere and it gets colder, all of a sudden the sky can all of a sudden cloud in, and that's what happened to us. We had perfectly clear skies up to the eclipse, but after the eclipse, often it'll cloud up like this. You can see the partially eclipsed sun there in the upper center there, and so we encourage you to go and see an eclipse yourself. Let's take a look at we're taking a look now at the partially eclipsed sun. We are getting back to I'm going to give it back to Sam here. Thanks for listening.
Thank you, Ron. And this, again, is the live view that we have from our telescopes in Chile. And I'm already seeing the sun is almost gone now. It looks like a crescent moon to me, actually. Not noticing a lot of sunspots or activity on there, but we'll learn a bit more about that in just one moment. Can we go to the Chile cam really quick? Because we're about 10 minutes away from totality, so I want everyone to be able to see exactly what our telescopes in Chile are seeing right now. Again, the sun is still pretty high on the horizon, and on this particular camera, we can't see the shadow. That's why we need the telescopes and the filters, but I'll bet that it's getting darker there based on the last one that I experienced. But during total solar eclipses, it's actually a really unique opportunity for scientists and researchers, because there are things that we can study about the sun that we can't do at any other time. So to come talk about a little bit more about solar science, Hakim is going to be joined by former director of the Teacher Institute at the Exploratorium and current CEO of Astronomical Society of the Pacific, Linda Shore. Hakim and Linda, tell us what you got.
Thank you. Welcome, Linda.
Thank you.
And welcome back to the Exploratorium. You're home.
Thank you.
Yes,
It's really
yes.
great to be back. 20 years ago, I helped host the eclipse from Aruba, which was fabulous. And it's really a pleasure to be back today to do this wonderful Chilean eclipse.
Wonderful. Yeah, let's do it.
Let's do it. Let's do it. So, Hakim.
Yes.
Yes. I was reading in Forbes magazine that this might be the last eclipse that scientists will need to travel to study the corona.
Yes, the reason why they're saying that is because we have so many assets. So NASA has space assets that are looking at the sun all the time and sending down data, as well as other space agencies. So here is from the 2017 total solar eclipse. These are not live images. And so you see the sun and the moon there. And here is the Japanese Hinode spacecraft.
And these are from space.
These are from space.
Wow.
And here is actually a rocket shot. So they actually flew a sounding rocket to coincide with the time of the total solar eclipse. And the thing is that during the total solar eclipse, from the ground, we get data all the way down to the sun's surface along the edge of the sun that we can't get at any other time. But we also have our citizens that are helping us out.
That's right. So there was a project called Citizen Kate. And Citizen Kate had 68 observers along the path of totality across the United States collect images. 61 of them actually managed to do it. And when those images were knitted together, this is what they got, this incredible three-dimensional view of the corona.
That's awesome. Many lines of sight equals 3Dness. But listen,
That's right.
There's still something for scientists to do, and some people really just got the luck of the draw where actually he made it happen.
Man.
This is Dr. Amir Caspi flying in a jet during the 2017 total solar eclipse under the shadow, so he gets a longer totality, and he got this data in the visible and the infrared while on that jet aircraft.
I hope he kept his eyes on the instruments is all I have to say.
Apparently he did, because here's some infrared white light combined. It's off on one side, so maybe he was looking at the sun.
Yeah.
So, you know what, though? There's still good ground-based data you can get, right?
Absolutely. This was done by who?
This is Druckmüller's software where he combined images.
So what we're looking at here is an image of the solar eclipse with incredible detail, because many, many images here are processed and put together in a composite. And I want you to notice a few things, because there will be a quiz later. You can see the moon, right? You can actually see a bit of the face of the moon. You also see the incredible corona, and the detail you're seeing is a trace of the magnetic field lines of the sun. Where you see the fanning in the upper and lower portions, that's the north and south poles of the sun, of the magnetic sun. And then on the sides, you see these incredible looping structures. This is when the sun is active. It goes through an active cycle in terms of its magnetic field and a quieter period. So let's take a look and see what a quiet and an active sun look like.
That's right. And you know what? The interesting thing about this is if you think about how strong gravity is.
Exactly. Yeah.
Gravity at the sun is 30 times. Here's another one of our live shots. We're almost at totality.
Don't worry. We will hurry up. We're not going to miss
right.
it. No.
We're not going to miss it.
Don't worry.
But what I was saying is that the matter on the sun leaves the sun and flies out into interplanetary space, even though gravity at the sun is so strong. So here now, we have an image of the surface of the sun during maximum, what we call solar maximum and solar minimum. Both are rotating.
Yeah, you can't see that in 2019 that image is rotating because you don't see any sunspots. Now, sunspots, remember those looping structures I showed you before? The sunspots are areas where the magnetic field comes out of the sun, makes a loop, and goes back in. And the reason the sunspots are dark is because these magnetic field lines kind of push the gas out of the way, making it just a wee bit cooler. And for a sense of scale, here we're looking at the sun. Here come the sunspots rotating along with the sun. And the blue thing at the bottom is the size of the Earth to scale. Amazing, isn't it?
It really is amazing. And where there are sunspots and where there are magnetic fields, there is activity. You don't see it in the visible so much, but when you look at the ultraviolet, the soft X-ray, you can see some of these different activities that occur on the sun, and sometimes they're explosive.
This is amazing. This is one of my favorite things the sun can do. This is called a prominence. Here you have that loop of magnetic field. The gases are following the loop, and this can last for days, weeks, even a month. Beautiful, and look at the Earth again.
Right.
Tiny in comparison to this thing.
And again, these magnetic fields are able to support this material, which must weigh tons against the sun's strong gravity.
Millions of tons.
So let's see some of that activity. What can these things do?
So look at that.
Wow.
So what we just saw here is one of those loops busting apart and sending out gas into space. It's a prominence ejection. This other thing here, if you notice this much more massive explosion, this is called a coronal mass ejection.
That's right. And what happens when they hit Earth, if they hit Earth?
Well, it can disrupt the electrical systems because you have this magnetic field, the magnetic materials then interrupting the Earth's electromagnetic systems, and you can disrupt electrical, radio.
More routinely when you take trips like you just did to Iceland.
Oh, yeah. You might be able to get an Aurora Borealis as well.
That's wonderful. Now there's the granddaddy of all activities. When these magnetic fields reconnect, they can also not necessarily send out matter, not send out mass, because there's an overlying magnetic field that constrains it. But you get this burst of light that we call a solar flare. And people actually did see those in ancient times in the white light, even though here we get it from space in the extreme ultraviolet. Yeah, it's happened.
That's amazing.
Yeah, it's really happened. So we're about 3 minutes, 2 minutes before totality now.
Can I sneak back in here with you?
Yeah.
Let's get cozy because I want a front row seat.
Yeah.
So the sun is just the thumbnail right now. We still have just a couple more minutes, but I am amazed at how different it already looks. It looks a lot richer, but I'm still not seeing those kind of prominences or those white lines hidden out. Why am I not seeing those yet?
Well, it is a quiet sun right now, so this is a solar minimum. So you won't see as many. We saw, for those of you who were noticing earlier today, or you want to rewind your broadcast, earlier today when the moon was making first contact, we saw an incredible prominence on the opposite side.
Yeah.
One thing I will say, down in Chile right now, when the sun is this narrow slit, the world around you looks very peculiar. It's not only dark, but everything is in super sharp focus because this thin line of light produces sharp shadows everywhere.
It's like a pin spot heading across the Earth.
It's exactly like.
Can we go to the Chile cam and see if we notice any differences there? That wide shot that we have on the top of the mountain. Okay, I feel like I'm noticing a difference. I do see sharper shadows on the ground. It looks cooler to me.
Down.
And we are lucky enough that we actually have a phone line out there on the mountaintop.
All right.
Executive producer Robin Higdon is on the line with us, ready to share what she's experiencing out there at the observatory. Robin, what does it feel like out there?
It is amazing here. Everyone is getting so excited. We're standing on the top of a very tall mountain. We're at 7,200 feet with a couple hundred scientists from around the world. It's gotten very dark. Just in about the last 5 minutes, the temperature has really dropped. We all had to rush and get our jackets on. The sun is just this tiny little sliver. The shadows on the ground are sharp and dark and very, very long. It's incredible.
And how many people are there? You said hundreds. Does that include scientists and other people from the community?
Right, there's about 200 people here. A
Look
lot of them
dark.
are scientists. There's 5 different scientific activities being conducted. They're repeating Einstein's 1919 experiment, amongst other things. There's
So-
a lot of photographers here, a lot of press, Chile TV, NPR,
Wow.
many other people. And
I
you
can
just
tell we're
feel
getting
the excitement in the air.
We're getting
close,
really,
close,
really
close here. We can
close
see the
now.
image on the screen. We're going to let you
That's right.
lead the conversation since you're there, experience it in person, Robin. But already the image of the wide shot, we can tell how dark it is, how red it is. It looks like sunset, but you still have some time. And
We're
I
a
don't know
minute
if we
away.
have a countdown, but I feel like I can see that moon almost
Yeah.
totally eclipsing the sun. And
We're
at that
very close. There's just that tiny sliver left. We are seeing sunset all the way around the edges here. We're getting a 360-degree sort of orange glow on the horizon. People are starting to yell and chirp here. Lots of groans of excitement. Oh, and there it goes. It's getting
Oh, there it goes.
All right.
I, this,
This is the good part.
my glasses on though. As long as I can see that little edge, I'm not going to take off my glasses, but it feels like we're just moments away. It's totally dark here now.
wow.
It's completely dark.
All right.
We've lost image. There it is.
There we are.
Beautiful pink Baily beads at the top of the moon. The corona is starting to reach out in 2 different directions, on the top and on the bottom. 2 very even, smooth streamers coming out. I can see a little bit of the detail in the streamers now. It's a beautiful, even coronal glow all the way around the edges. I can now see one of the planets. I don't think you can see it in our telescope image, but I'm seeing planets and stars starting to emerge. And again, the whole horizon is glowing orange and yellow. The streamers are reaching out. It's gotten very still here. Actually, people have stopped yelling and screaming, and I feel like you could hear a pin drop.
There we go. There's a prominence.
We have a nice close-up view of that prominence in the side of the sun there. It must be incredible seeing it from the ground.
If you can see it.
Absolutely beautiful.
Yeah.
That's big. That's a big one.
So this is close to what we
over-
saw on the models. They took the filter off the telescope so we can get that kind of white light, what our eyes can see without any glasses.
And that's the one we saw earlier when the moon was making first contact, and we were saying, oh my gosh, we won't see that again until totality, and here it is.
Robin, can you tell us how this is different from...
I've seen several eclipses. This one is very dark. It's very, very dark here. The sky is a deep, deep dark blue, and right where the moon is the darkest black I've ever seen.
That's
Pitch
because
black
of the
in center.
altitude.
That's the altitude.
Hakim, what was that?
No, that's because of the altitude. At 7,200 feet, you don't have the rest of the atmosphere shining light on you, right? The molecules in the atmosphere. So it's almost like you're in space.
You are now
I
closest
feel like I'm in space.
It is absolutely gorgeous on the monitor. I can't imagine what it's like
Yeah, you
being
can
there
see
in
the prominence
person.
at the
I
bottom.
feel like we're seeing a little bit more light coming around.
See the prominence at the bottom?
Yeah, yeah.
We are.
It's a lot
So
of
I'm
red
seeing
glow.
Baily's
5
beads
o'clock.
now. I'm seeing some bright pink emerging. I am actually, there's
Oh.
The diamond ring.
Here it comes.
absolutely beautiful. I have to put my glasses on, unfortunately, because
Please
Wow.
do.
a beautiful diamond ring.
That was beautiful.
Bright white light.
Wow.
Oh, look at
And we are getting a beautiful shot, wide shot of the
Look how dark it
observatory
got.
up there. It looks like it's past sunset there, but in just a few
And there's that
moments,
planet.
the light's going to come back
that
on
it?
the Earth.
Yeah, yeah.
So
I
that-
think, or is that a
That's
light?
right.
I can't tell.
It's already lightening up here.
Yeah, we can see that. It's what I'm amazed by is you really get a sense of how quickly the moon appears to move. It does move, and also appears to move based on the rotation of the Earth. That just flew by. You could have fooled me that was much faster than 2 minutes, but that was about 2 minutes and 40 seconds, wasn't
Wow.
Yep.
It was incredible. I can literally see that crescent now growing. Like, just it's getting bigger and bigger and bigger with every second. The moon is truly moving fast.
Well, I am envious of where you are, Robin. Thanks so much for bringing the telescopes and the crew out there
Thank
to
you.
bring us up live from Chile. We'll talk to you when you get back and hope you travel safely. And the audience here is also going wild. So I gotta say, we've all seen total solar eclipses in person. You've seen more than I have, but even from the one I've seen, this one was markedly different. Can you tell me about your past experiences, Linda?
Well, I've had 2. One was in Indonesia, which was my first, and it was very cloudy, extremely cloudy. We were lucky. We did manage to see totality, which was spectacular, but that moment of of that skinny bit of light with every single cloud being sharp was amazing. And of course, the 2017 eclipse across America was breathtaking. This one, I think, was interesting for the reasons that Robin said, that being as high as she was, the sky was incredibly dark. And so in both the eclipses I was at, I can't say it was in a super, super, super dark blue.
Yeah, and we're going to get to see an eclipse over South America in 2020, right, Hakim?
Yep, that's right. And next summer, that's the case, right?
Just next summer, yes.
Yes. So I've seen 4 in 2006 from Ghana, 2010 from the South Pacific and Mangaya, 2012 from Australia, and then 2017. And the local climate matters, the altitude matters, but also what's really cool and interesting is the animals in that location. So the very first one I saw in Ghana, when it got dark, the nocturnal animals came out, and that was just made everybody go crazy.
That sounds incredible. So next year's a total solar eclipse in South America, and don't forget, in 2024, the total solar eclipse comes back to North America.
That's
it's going to be sweeping up through the Northeast. So we know when eclipses are going to happen. Thanks so much, Hakim and Linda.
You're very welcome.
How do we know when the next solar eclipse is going to happen? Well, a lot of observation has to go into that. So Exploratorium educator Paul Danstep is here to tell us a little bit about some of the ways that we can predict these cycles of total solar eclipses. Thanks, Paul.
Sam doesn't have an earpiece?
Hi there. So having seen Totality, now we can ask ourselves, how did we know this was going to happen? So human beings have been predicting eclipse events for thousands of years, since before we knew the Earth was orbiting the sun, since before we knew that the moon moved in an ellipse, since before we knew any of the fancy stuff we know now. So I want to show you a way of predicting eclipses that can be done just using ground-based observations of how the moon moves in the sky. So I have an image here of the sky right before a solar eclipse, and if we look at this, we can see...
Is the remote on?
Yeah. So this is during a total eclipse, and when one of these is happening, we can ask ourselves, when will this happen again? So immediately after an eclipse, we have 2 things in the sky to think about. We have, first of all, the sun, and then the moon, which is right next to the sun. It just drifted past it. And over the course of the next day, the moon's going to keep drifting, and it's going to get about this far away from the sun. So given that drift speed, we can predict that it should take about 29.5 days for the moon to make a full lap around the sky and meet up with the sun again. So let's follow the moon day by day as it goes through its monthly cycle. We can see it hit each of its 4 phases, and after about 29.5 days, it's going to be back in the vicinity of the sun. But we're not going to see an eclipse because, as Eric Muller explained earlier in the program, the moon has some extra motion to it. From the surface of Earth, what we see is, in addition to the sideways travel of the moon also seems to be going through a kind of subtle up and down motion. So in order to cause an eclipse, the moon needs to be vertically aligned with the sun, and it crosses this line once every 13.6 days, completing a full up and down cycle after 27.2 days. So let's start with an eclipse and now follow the full motion of the moon as it makes its way around the sky. It completes its up and down cycle after 27.2 days. It catches up with the sun after 29.5 days, but it's now 2 days into its next up and down cycle, causing it to miss. If we follow it for another lap around the sky, we see that things get even worse. It completes its second up and down cycle after 54.4 days, but doesn't reach the sun till another 5 days after that, missing by an even wider margin. So if we keep our attention on the sun, we'll see the moon fly by every 29.5 days, and there's some near misses, but a total eclipse won't happen again until the up and down cycle matches up with the around the sky cycle. They do eventually come back into sync after 6,585.3 days, or 18 years, 11 days, and 8 hours. If we look down on the Earth during an eclipse, like this one, which happened in America in 2017, we see the shadow of the moon cut across the Earth's surface. And anyone standing in the path of that shadow will witness an eclipse and will be able to predict that there should be another one in 18 years, 11 days, and 8 hours. So let's fast forward 18 years and 11 days. Now, this next eclipse won't start for another 8 hours, and during that time, the Earth continues to rotate. So when the moon's shadow does cut across the Earth's surface, it's going to do so in a different location, this time cutting across China and heading out into the South Pacific. 18 years after that, a nearly identical eclipse will cross North Africa into Southeast Asia. So this repeating family of eclipses is known as a Saros cycle. So these are all eclipses from Saros number 145. Every eclipse belongs to some Saros, and there are currently 40 active Saros cycles, each spitting out eclipses on a repeating 18-year schedule. So if you look at a map of eclipse paths, like this one showing all of the eclipse paths from 2001 to 2025, you can often spot pairs of eclipses that belong to the same Saros. For example, these two paths look really similar, and they're about a third of the way around the Earth from each other. And if we look at their dates, we can see that this one happened in 2003, and this one will happen 18 years later in 2021. This is a pair of sequential eclipses from Saros number 152. So 18 years ago, this eclipse happened in South Africa, and the eclipse we saw today is the next sequence the next eclipse in Saros number 127. So getting back to our original question, when will this happen again? We can predict that there's going to be an eclipse 18 years from now in 2037 crossing Australia. So those are the basics of this ancient method of eclipse prediction.
Thank you so much, Paul.
Sure.
That's so interesting. So the eclipse we just experienced is kind of like a sibling or a cousin of what we saw in Zambia in 2001.
Yeah, we've covered every kind of eclipse currently available, and now we're just running through the catalog again.
And they're almost the same, so you might call it a syzygy similarity.
You might call it a syzygy similarity.
I will. Thanks, Paul.
All right, take care.
So you can already see back on the telescope live from Chile how much of the sun has already reappeared. The moon is continuing its path. And we often talk about the moon as the instigator of the eclipse, but we can't forget the star of the show, which is the sun. And there's so much more that we have to learn about the sun. So we're joined now by NASA senior educator Eric Christian to talk with Hakim about some current solar research.
Eric, you're the star of the show, man. Forget what he said. All right, so tell us about what you're doing with the Parker Solar Probe.
So last year, NASA launched Parker Solar Probe. It was an amazing night launch of a big rocket, the Delta IV Heavy. You can see here on the screen. And this is our first mission to the sun. We're actually going to go to within 4 million miles of the surface of the sun. Go to where the action is for the first time.
Wow.
And measure some important things about the sun that we've been wondering about for 50 years since NASA started.
Yeah, you can wonder about it and observe it from a distance, but there's nothing like being there. But really, it can get really hot close to the sun. So how do you deal with that?
So that's one of the reasons why it's taken us more than 50 years to get this mission done. We needed the technology to catch up to where we could actually do this. There's an enormous heat shield on the front of Parker Solar Probe. You can see it here, the big white octagon. That protects us from the sun. My instrument and most of the spacecraft hides in the shadows behind that heat shield. And it's because of that heat shield that it's new developments. It's carbon foam, carbon fiber. It's only now that we can do this amazing mission, our first mission to a star.
So it takes sunscreen to the next level.
Oh, yeah. It's SPF millions.
There you go. What are we looking at right here now?
So as one of the problems with this mission is that when we're doing the most interesting science, when we're close to the sun, we can't communicate with it because the sun is a source of radio noise. And so it's like trying to talk to someone who's standing next to a loud band.
Signal-to-noise ratio.
Right, exactly. So even when it's close, Parker Solar Probe sends out a single tone, a single note that lets us know it's okay. And every day or two, we can get there. This is one of our first images. We've actually got a camera on Parker Solar Probe called Whisper. It's two cameras aligned with each other, and they look off to the side, because if they looked at the sun directly, it would get completely fried. And so this is looking at the streamers that you see during
And what's that
solar
bright dot there?
So that's probably a star, and there's some artifacts to it, but it's really the streamers that we're flying through.
Wow.
Parker Solar Probe will take pictures of the corona as we fly through
It's like you can taste the sun.
Yeah, it's going to be great.
Delicious. A little spicy though.
Yep. And so I'm going to be, my instrument measures particles from the sun. We've got another one that measures the solar wind. We've got instruments that measure the electric and magnetic fields.
All right.
This is really exciting. We're starting to get data. We launched last year.
Wonderful.
We're starting to get data. We still don't understand the data. We're working on our first scientific papers, but this is going to be
For
over
next
the next
year's
6 years.
Eclipse, you can give us an update. Last time we did this, you hadn't flown yet. Now you're up there. So
Everything's
let's see what the
working.
sun looks like right now.
Yep.
What is going on there?
So
Thanks, Eric.
Thank you, Eric. Thank you, Hakim. We are getting closer to the end of our broadcast, but I want to say there's still lots of exciting science being done. We talked a lot about what we saw, the prominences coming out of the edges of the sun that we could see sometimes during eclipses, and we heard that those are caused by magnetic fields. But the sun isn't the only celestial body with magnetic field. So here to talk with me more, we have Troy Klein, also with NASA. He'll give you his official title, who's been working on some missions that help us explore the Earth's magnetic fields. Hi, Troy.
Oh, it's a pleasure to be here with everybody. Actually, I'm Troy Klein. I come from Goddard Space Flight Center, and the job I do there, I have two jobs. One is the director of the STEM Innovation Lab, which is a wonderful space where we create maker activities, much like they do here at the Tinker Space here at Exploratorium. But my other job that I had before that was working with a magnetospheric multi-scale mission, the MMS mission, and that's a very interesting mission, which is why I'm here today.
Great. I think we have a video. We'll get that going now to kind of see what involved. And so this launched in 2015, yeah?
That's correct. And what people tend to forget is the sun and the Earth are both gigantic magnets. And as a result, they have enormous magnetic fields that often collide and interact with each other. This mission was launched in 2015, 4 identical satellites, exactly like the one you're looking at right now. And they were launched on top of an Atlas V rocket. They're currently in orbit around the Earth, flying in a tetrahedral pattern that we'll see in just a little bit. Now, what they're looking for is where the magnetic field lines, often of the sun and or the Earth, come together and collide, and often the Earth's own magnetic fields, because of all the activity in space, collide and produce that enormous invisible explosion that you see right there.
So in this animation, those lines are highlighted red and blue, but it's not actually visible to our eyes.
That's correct, which is why there are 25 different instruments aboard each one of those satellites. And here is another example of the magnetic explosion. Now, when that happens, enormous amounts of energy are released into the north and south poles, which create the Aurora Borealis and Australis. And here you see the formation pattern. Now, one of the really interesting things is we have 4 satellites because we want to capture that data in 3 dimensions. And in order to do that, you have to have 4 points of view. So if you had a soda can in the front of your table in front of you and you wanted to capture the top, the bottom, the sides, and all of it, you would have to have 4 different points of view to capture it in 3D. That's what MMS has done successfully multiple times, and this mission is actually changing the way we understand magnetism. And it's this magnetic structuring that we see around the sun that creates the shape of the corona and of coronal mass ejections and so on.
So this has been collecting data since 2015. It's still coming in, and we're still learning lots from this mission.
That is absolutely correct. It's so successful, and congratulations to everybody out there that's on the MMS team right now.
But it's not just for NASA and just for hardcore research scientists. This data can be available, right?
Thank you for asking that, because what we do is, part of my job is taking the massive amount of information that we get from our scientists and engineers and try to turn those that data into something that's usable by us in the public. And many of you may have heard about the Maker movement, which is really sweeping the nation and the world. NASA is listening to that as well, and we've decided to create maker spaces, and one of them is at Goddard Space Flight Center right now. And in that maker space, we have virtual reality, we have 3D printing, coding and electronics, you name it. And we're recreating some of those data sets in virtual reality, so you can actually fly through real data sets of the magnetic field.
Wow, that sounds incredible. But just being honest, would you rather experience the magnetic fields around the total solar eclipse in virtual reality or in real life?
Hands down, virtual reality. No, I'm just kidding. No, absolutely. I've been in, this counts, so this will be my 4th eclipse to experience with, and 2 of which was with the Exploratorium.
Yes, and we're happy to have you as a partner. Thanks so much, Troy.
We'll
see you next time. That being said, we now have more chances to view total solar eclipses from the path of totality. As mentioned earlier in the broadcast, the next total solar eclipse is also going across South America. You can see in this map that we're going to put up that it is a little bit more south than the one that we saw today, but also going through Chile and Argentina. What's most exciting is in 2024, you see the path of totality crossing back up through Mexico and up through the northeast of the United States. So North America will get another spectacular total solar eclipse, and we invite everyone to come and check it out. It's one of our favorite phenomenon. And though we're beginning to wrap up this particular broadcast, this is just the beginning of some of the fun we're having at the Exploratorium. July marks Moon Month. So all month long, we're celebrating all things lunar. You can see there in the middle of our museum, we have this giant, topographically accurate sculpture of the moon. It kind of looks unbelievable, but it's there. It'll be with us. And around it, we're doing programs, performances, lectures, culminating on July 20th, where we're taking a full day to celebrate the 50th anniversary of the Apollo 11 landing on the moon, which is an auspicious anniversary because as of now, NASA is working on its next lunar mission, the Artemis mission, which intends to put both men and women on the moon and let's give it up for that, and teach us so much more about what it means to live out in space and possibly act as a potential launch pad for people and astronauts and instruments to be living on Mars. So keep an eye out for that. Before we end, though, I want to give one more big thank you to all the crew and talent both here and in Chile, especially the staff of CTIO who helped make this all happen for this particular broadcast. I look forward to seeing you all underneath the shadow of the moon. So from Pier 15 in San Francisco, I say adios and stay curious.